Some more words to describe movement using physics terms are levers or levers, you may have heard them called, pulley systems that we're going to examine, something called the wheel and axle, and then the incline plane, which is pretty much what it sounds like, an inclined surface like a ramp that we're going to discuss how changes make motion or movement easier or harder. Levers are another thing that are difficult to explain in an audio file, so we're going to go over those in class. We're going to learn about first, second, and third class levers and talk about what those look like in the human body. It is important that you do the reading before class so that your head is not spinning too much to understand what a force arm is, what a resistance arm is, and really understand how changing those affects motion. For each of the classes of levers, first class, second class, and third class, I'm going to draw some diagrams for you in class. But you may want to take a look at those also in your textbook before you come to class. You're also going to learn that the third class lever is actually the most common lever in the body. Just in a nutshell, the first class lever could be described kind of like a seesaw. The second class lever is described in terms of how what a wheelbarrow would work in terms of a lever. The third class lever would be defined as a screen door, and I'll explain that more when we get into class. I've added a slide here about mechanical advantage to explain a few other things to you about levers. Mechanical advantage is the ability of the force arm and resistance arm to be balanced, or for the force arm to overcome a certain amount of resistance. Just a few things to know and understand. We will go over this in class. Balanced mechanical advantage is equal to 1. So in whatever unit of measure you're using, but for the sake of ease, we're just going to use some simple numbers. If your force arm is equal to 2 and your resistance arm is equal to 2, 2 over 2 is equal to 1, which would create a nice balance. And I will show you this in reference to something like the first class lever or a seesaw. A poor mechanical advantage would be when a resistance arm would actually be greater than a force arm. So if we're using measures again for the sake of simplicity, we just use some simple numbers. Your force arm was equal to 1, however your resistance arm was bigger and it was equal to 2. That would be 1 over 2, or 1/2, which is less than 1, and anything less than 1 produces poor mechanical advantage. Now, if you have the force arm greater than the resistance arm, that means that the actual power or the force is actually greater than the amount of resistance, so that allows the resistance to be overcome by the force, which is good. When we think about the human body, we think about forces being muscles and resistance being weight or a pull of gravity. If our muscle is stronger than the amount of weight that is being challenged by that muscle, that's a good thing. If our muscle is weaker than the amount of resistance that is challenging that muscle, that's not so good. We're also going to learn about the axis, which is the center between typically between the force arm and the resistance arm, but there's some variations to that. The axis is the point around which movement occurs in the human body. That would be the joint. Pulley systems we're going to see from time to time in the human body. We're not going to spend a lot of time talking about those today, but what is important to understand is when there is a pulley system, it actually improves the mechanical advantage of the force that's pulling. Basically changes the direction, redirects the force, and creates more ease in moving the same amount of resistance. So as you might be familiar with when you go work out, and you use wall pulleys, you'll find that it's much easier to pull that resistive weight across an axis into a different direction using a pulley. There's a good example on page 119 in your textbook, figure 8-34, that shows the ankle joint and how the lateral malleolus acts as a pulley. So it helps the muscle actually have a bit more force to be able to pull across that joint, it changes the direction. We're going to learn also about the knee and how important that patella is, that kneecap is, to actually redirect the force and create more strength in your quadriceps muscle, and how the absence of a patella is a pretty bad thing. If you were to crack your kneecap and have it removed, you would have some slack in your muscle, and it would make it much more difficult to fully extend your leg. The wheel and axle description of another type of simple machine is a way of describing how, if we take a lever and we actually we increase it in length, it actually increases the ease of being able to create movement. So probably the best example that I can think of is taking a very long wrench to take off, that's probably not even the right word, to take off the bolt when you're changing a tire. The longer the wrench, the easier it is to move that very tight bolt. If you were to use a very short little wrench or lever, you'd have to use quite a bit more force in order to create that movement. So it is a way of creating movement, again, around an axis or a center point by changing the length of that lever. And there's a good example in your book on page 120, figure 8-38, where you can see a faucet handle and how we use that many times for people who have some potential loss of strength. It makes it much easier to turn the faucet on and off by having that nice long lever. Okay, so the last term that we're going to discuss today is related to something called an inclined plane. Basically, inclined planes help you exchange an increase in distance for a decrease in effort. And the best example is looking at a wheelchair ramp. If the ramp is longer, it means that the rate of incline is much less and requires definitely less force, whereas a shorter ramp would require more force. Now, I think that one thing that's kind of worth mentioning here relates to ADA and what ADA requires in terms of the length of a ramp. If you are installing a ramp on a building and you are following the ADA requirements, what we know is that for every inch in height that you need to travel, you need to also make the ramp a foot of distance. So a typical step is 8 inches, and that means for each step of height into the entrance of a building, there needs to be 8 feet of distance, which is why we see the ramps wrap around and zigzag back and forth, and they can be pretty unsightly sometimes if you put them on the front of a house. So a lot of times people will put them towards the back because they can be pretty lengthy and take up quite a bit of the front yard area. It is important to understand, though, that the most ideal incline of a plane would be, for if we look at ramps, would be 1 foot out for every 1 inch up.